All right. Well, welcome back, everybody. We're going to keep working on this lightsaber some more. And hey, look at that, some spam. Fantastic. Give me a sec, software's running slow. I'm just going to ban this person real quick. There's no need for that crap. All right. Well, we're going to be working on this lightsaber some more. So, a couple orders of business first. I wanted to start thanking new followers that I get off stream. Obviously, I thank the ones that start following me while I'm on the stream because the alert pops up, but I don't always spend the time to thank the ones off stream. So this time, just one, XSark or EK Sark. Thank you so much for the follow. I really appreciate it. And we are going to keep working on this lightsaber. Obviously, we still have the Dogecoin bounties in place. I have some ideas for a system or a reward system or a way of organizing the work better, actually. That's a better way of putting it, so that people can help me. So I'm going to start trying to set this up in such a way that I can create tasks and people can see that even while I'm not streaming necessarily, and try and give me ideas or even complete those tasks and complete parts of the projects. And I hope that that will help speed up development some and at least make it more interesting for you all too, because it give you a way to interact and possibly even get rewarded for it. Ideally, that's where I'd like to end up. So I'm thinking through a lot of that stuff right now. Uh, Obviously, the goal with this whole channel is just to kind of pioneer a new form of development, and it's not necessarily to be entertaining or get lots of viewers or make money or anything. It's just I want to change. I want to offer a new option for development. I want to offer something that I think could be better, a better process. So if you have ideas regarding that, absolutely throw them my way too. I'm willing to consider just about anything. But yeah, that's all pretty much I got to say about that. So let's get started. The current bounties make me laugh. That's an obvious one. Tell me about a cool project you're working on. That's a really awesome one. I haven't had many people take advantage of that, and I love to hear about cool projects. And then also, if you can find a cheap way to machine a custom metal hilt for the lightsaber, that is worth 5 Dogecoin, and honestly should be worth like 5,000 if somebody can figure that one out for me. But I just don't have that much Dogecoin to give away. So, all right, let's get started here. We're working on the recharge circuit right now for the lightsaber. So let me pull up our diagram just to recap where we are, because I know it's been a little while. We're working on this part. This whole thing here is the recharge circuit. We have the USB-C port, a voltage boost, then the actual recharge circuit, and then our connectors and our batteries are going to be off board, obviously, plugged into the connectors. So right now we're working on the voltage boost part, and I think we were almost done with that. We just had to decide one last part, which was an inductor, and I think it had to have a fairly high inductance, and I didn't totally get a chance to work through all the math because it was fairly complicated. So that's going to be step one, is figuring out all of the math related to or working through the math related to that. There's a way you calculate what exactly you need for that inductor, and it's in the data sheet. Also, I apologize if looks like the quality of the stream is pretty good right now. I apologize if it has issues tonight. It seems that Windows Update is working against me here, so. And I know copyright rules are probably the biggest problem right now for most streamers, but I also firmly believe that Windows Update is a good contender for the biggest obstacle that streamers face. So let's see. All right, let's open up this data sheet. All right. Okay, here we go. And then we want... Is this the right part? This is... Advanced linear. No, this is not the right part, I don't think. Nope, I clicked on the wrong one. I need the voltage boost. That's the battery charge thing. Battery advanced linear charge management IC. That's the thing that controls how and when the batteries charge. But in order to charge the batteries, I need a higher voltage, hence the voltage boost. Voltage booster. Voltage non-synchronous boost converter. Okay, this thing. We're using this simplified schematic, and we need to decide L1. That's the only part we don't have. Everything else is here. Oh, I did note here, we would do want to fix this. Oh my gosh. My computer's running so slow. I apologize. I really, really hope this isn't affecting stream quality too bad. If it is, let me know though, and I'll see if I can do it. I don't know that I can do anything about it, but I'll try my best. Okay. So that doesn't have a value to it, but we did add a value to the bill of materials. Here it is. So bill of materials right here looks like our value is 10 10 microfarads. Sorry, I choked on some air. And we have a part picked out. Okay. Let's check this one out. Capacitance 1 microfarad. So this has a capacitance listed for this one. Do I not have this part listed? It's not in my bill of materials here, which is kind of distressing. I have R1, R2. Yeah, I don't have C2 listed in this bill of materials, or U1 actually. So that's not good. And I wonder how that happened. But we do have a part. Like, we have this part number here. So let me look that up real quick. Okay, looks like we're going to be doing some housekeeping to get everything where we need it to be. So let's pull the bill of materials up. All right, C2. Man, this is running slow. Okay, so part number, description, link, and value. 1 microfarad. Okay, so that's a little better. Yeah, keep current format. Oh my gosh. I think in an ideal, I know a lot of people, there's probably a lot of different variations of a streaming setup, but I think in an ideal world, I get a separate computer for doing the actual streaming that I'm doing the work on. So like do the work on one, pipe that video into another computer, which then actually streams it. And that way you can split that up. Might make it easier to manage performance issues. All right, so that's sorted out. And then the other thing we need to add is this actual part. So let me see if I can find it on DigiKey or something. TLV 61048 dBVT. Yep, this is it. All right. And then we said this is U1. Value is not available. Okay. Really? All right. Description. Part number. And link. I cannot wait to see how expensive all these parts end up being. It's probably going to be a lot. Okay. Inductors are typically L, right? Yeah, L1. All right. Cool. So now we have that worked out. Oh, we need to add a variable here. Capacitance 1 microfarad. So how do they do it here? Capacitance 1 microfarad. Okay. We're just going to add a property. If we can. I think we can. Oh, man. Parameter. Capacitance. I'm surprised this isn't one already, you know? And we'll show that. Okay. And look at that. We have our little capacitance thing. So for this stuff, for like capacitors or resistors, I don't like to have the part numbers, but I do like to have the values so I can get kind of an idea what's going on. And then chips have the location and then the part number. Okay. How do we calculate L1? Let's see. Inductor selection is the most important component in the power regulator design. So we really need to get this one right. There are 3 important inductor specifications: inductor values, saturation current, and DC resistance. Designed to work with inductor values between 2.2 and 10 microhenries. Okay. That's kind of a lot, but that makes sense for something supplying this much power. To calculate peak current of the application inductor, or use equations 2 to equation 4 to calculate the peak current of the application inductor. To calculate the current in the worst case, use the minimum input voltage, maximum output voltage, and maximum load current of the application. To have enough design margin, choose the inductor value with a 30% tolerance and a low power conversion efficiency for the calculation. In a boost regulator, the inductor DC current will be calculated with equation 2. Okay. So, first things first, we have to calculate this, which is the max current. So, I think... Oh, here, I'll just leave it up right here. Okay, so V out times I out. I think we decided, let's see if we can do 1 amp. That would be kind of good if we could do that. Times 8.4. Whoops. Not 80.4. 8.4. Okay. So we'll store that in memory. So 8.4 for the top, and then V voltage in. 5 times 0.8, because they said use 80%, and we need 5 volts from the USB. 4, store that in memory. I know this might be a fairly easy one, but all right, and then 8.4 divided by 4. So we get that our I under load here is 2.1 amps. I don't know if we can supply that. we'd have to have a lot of current coming into the, like, IN would have to be really high. So I don't really feel good about that number. I feel a lot better with about 500 milliamps going out. Doing a really slow charge. That's a really slow charge. Yeah, let's do that. Let's run the numbers again. Oh. Okay. So 8.4 times 0.5. 4.2. Store that in the memory. Our VN times efficiency used to still be 4. So 4.2 divided by 4 is 1.05. I feel a lot better about that number. So that's the inductor DC current. All right, the inductor ripple current is calculated with equation 3 for an asynchronous boost converter in continuous conduction mode. Okay, so we're going to have to save this. All right, let's calculate this top thing. So V in 5, well, actually, let's get the part in the parentheses first. So V out is 8.4 plus, oh no, we're doing 12, right? 12 volts out. Yeah. Hold on, I think we did this math wrong. I think I'm planning on doing this. I think I've calculated this for 12 volts out. So So 12. All right, so we're doing it again. 12 times I out, which is 0.5. Divided by 5, so divided by 4. So 1.5 is our I load. I'm sure I'll end up doing this like 5 times before the end of the night. All right, inductor ripple current, equation 3. All right. Maybe this will tell me too if this is like even possible. All right. So V in, or so we got V out, so 12 plus 0.8 plus, or minus V in, which is 5, equals 6, or 7.8. Yes. Times V in, which is 5. So the top is 39. Okay. And then the bottom is the inductor value divided by the switching frequency. All right, let's figure out the parentheses part first. So V out, oh, okay, so that's just 12.8 again. So 12.8 times, what is our switching frequency? This is determined by the frequency pin. We leave it floating, so it's 600 kilohertz. So is that 600,000 then? I really wish I had an example of this. I guess it'd be 600,000. Because we are using microhenries. Okay, I guess that kind of makes sense. So times 600,000. multiplied by the inductor value. Let's just say we pick something that's 2.2. Hold on. Microhenries. So 0.0000022. I think it's 16.89 amps of ripple current? Right. Maybe let's use 4.7 there. So 768,000 times 0.000047, because that's a common value too. Oh, well, I guess that technically makes it worse. Oh, no, but we forgot to divide. Okay, so use that value and then do this value divided by this value is equal to 1.08. That's our inductor, our ripple current. Therefore, the inductor peak current is calculated with equation 4, which is the original thing here, which I think we decided was 1.5, plus this divided by 2. 2 equals plus 1.5, 2.04. 2.04 amps. Normally, it is advisable to work with an inductor peak-to-peak current of less than 40% of the average inductor current for maximum output current. A smaller ripple from a larger valued inductor reduces the magnetic hysteresis loss in the inductor. The response time is increased. Table 2 lists the inductor for 600. Typical saturation. What's saturation current? Is that this top one? I mean, they're obviously using big stuff, so... Alright, well, let's see if we can find something then. Let's go to DigiKey. Let's look up inductors. Fixed inductors. And in stock, active, it's only 23,000. And then 4.7 microhenries. All right, well, there's a fair few at least. Most of these are pretty big, though. Here, let me show you. Like, they're not these little... There's only a couple that look kind of like this, which are... But even these aren't that small. $25.20. Jeez. 10.08s. Most of these are these big things. Big wire wrapped ones. I think I need to get a pretty high saturation current. I don't know what saturation current is. That term wasn't used anywhere except right there. We know that our peak current is 2 amps. What is... Let me see if this shows up anywhere in this data sheet. Saturation. 3 important inductor specifications: inductor value, saturation current, and DC resistance. Turn the peak current of the application. To calculate the current in the worst case, use the minimum input voltage, maximum output voltage, and the maximum load current of the application. To have enough design margin, choose the inductor value with minus 30% tolerance. Right. I have a feeling that, oh man, whatever I pick here, I should pick something where I can adjust it later, where other parts will fit on that footprint in case I mess this up. All right, I'm gonna Google this or search it. Saturation current. Some manufacturers will rate their parts for a 30% drop in inductance. Okay, hold on. I'm learning here. What is there? Current rating is the maximum current the gauge of wire used the inductor can handle at the rated temperature range. Okay, that makes sense. Saturation current is the point where the magnetic field no longer increases proportionally with an increase in current. The core has become saturated. Operating at or above saturation current, temperature derating should be considered. Okay, so I don't care as much about saturation current as I do current rating. Okay. I think this works then. It looks like those little parts are not going to do it all. We're going to have to get something fairly sizable. So I got to find something in Circuit Maker. So I've got a list of inductors here. I got to find something that will work. Really? Is there an option for an 0805 part that fits this? That's kind of surprising, honestly. Let's go with current rating. Let's go with 4 amps. Now what kind of parts are left? Okay, all the weird parts. So nothing like standard size. There's also a through hole option here. How many parts are left with that? 31. Oh, that's cool. I think I'm going to go surface mount. As much fun as it'd be to do a big through hole part. Right. Let's try not to buy anything that's like $9. It's got to have at least cut tape. Okay. Here, I'll pull this on screen just so y'all can see what I'm doing. But I'm just trying to find the best option here. So obviously there's some really cheap stuff, but you have to buy like, yeah, the minimum quantity is 1,000 or 10 or something. We can't really do that. So let's see. Box, bulk, cut tape, strip, tape and box, tray tube. All those are fine. Is there a thing where I can change the minimum quantity? Nope. I don't want to get something that's like... that looks interesting. How big is it? 6 by 6 by 4.5. Okay, not ridiculous. Oh wow, the unit price really is 46 cents each. That's cool. That was this one. 20%. Current rating is 4.2 amps. I think that would be okay. I guess next thing then is just let's see if we can find any part. Even change this. All right, let's see. Let's just start looking through these and see what we can find. Ah, no model. Well, that's a shame. I'm trying to pick stuff that I've like have some, at least from companies that I've used before. Nine 2.4. It was talking about how much this DC resistance mattered, but then it doesn't like tell you how to pick it. I need to try and pick something that was going to be semi-easy to solder to. So, and some of these are looking pretty tricky. So microwaves, 5.1. Interesting. This Murata part looks interesting. Nope, no model. All right, this is going to be tough. Nothing. All right. Let's just do a general search here. Passive components, inductors, fixed inductors. Right, so there's a lot. Is there a way to like filter this, or do we just search like everything? Yeah, it's looking like we're just searching everything. All right, cool. Could always pick this one and use. I have the similar one over here. Let's see here. Nope. I wonder if I just start going down this list until I find one. I mean, all of these should more or less work. Hey, this one has a part number, a model and everything. Hold on. 22 mega ohm. Okay. It's Abercon LLC part. Let's use it and see what happens. Why not? Place. Drop this right there. Don't need anything else. Okay. Let's go back to our circuit here. All right, needs to be between VN and SW. Conveniently enough, these top two right here. All right, so let's... Oh, come on. All right, we can turn off the part number. Yep, hide that. Does it not have... Really? Doesn't have the inductance? .7 microhenries. Okay. Oh, I thought I turned the name off. I did not. I just locked it. Okay. Okay. This part is done. Yeah, should be good. Is this... I've labeled this AV4, but I feel like... I thought we set this voltage divider up to be 12. Hold on. Let me double check this data sheet. Excuse me. Is C2... Okay. Are these both 1 microfarad? I feel like we didn't do that. $10 microfarads for C1. Yep, okay. I apologize. I'm all over the place tonight. I know that. I'm just trying to make sure I catch everything. Okay. So I made the mistake of scrolling down in this data sheet and found this schematic, which is much more like what we're actually doing. Yeah, this are literally the same thing. So I'm trying to make sure that we did everything right. Don't need the layout stuff yet. I need to know how to pick the resistors, though. Selection. Okay, there is a way to do this, I know. Here it is. V out divided by V ref minus 2. V ref is 800 millivolts. So $12 divided by 0.8 equals minus 1 times R2. What's R2? Is that the lower or the upper one? It's the lower one. I have them backwards here. Times 154 kiloohms. Oh, I might actually have this set for 8.4 volts. That's really interesting if I do. Because that math definitely did not work out. So, well, this is just a voltage divider. I could probably figure most of this out, right? So 8.4 divided by 8 equals minus 1. I don't know. That was wrong. 8.4 divided by 0.8 equals minus 1. All right. Times 154 kiloohms. It's 1463 mega. Okay, yeah. So this is an 8.4 volt converter. That makes sense. No reason to boost it higher than that. We can always adjust that later if we need to. All right, I think all of that works then. All those parts are good and solid. So that means that we are done with that section, and now we need to move on to. So we've done the converter, the boost converter. Now we need to do the recharge thing. Which this is going to be a whole lot of fun. I really hope this part is already made. Low dropout linear 2-cell lithium-ion battery charge controller with something. All right, let's try and place this part. So part number is this. Does it not exist? Ooh, that's interesting. Do we have to actually like make a full custom part? All right, let me pull up the bomb. Actually, let's just go ahead and find it on DigiKey and add it. And then go from there. Yep, okay. In stock, everything. Yep, that looks like the right thing. All right. Oh, we didn't add our inductor in. Crap. That's really bad, actually. All right, let's add this part in before we forget. Fun fact, Control-Shift-T will open up tabs you closed in Chrome. If anyone didn't know that, that might save your life one day. Okay. Now we're gonna add this this new chip in. Description. Okay, and there's no value associated with this. And this is going to be U2. All right. And it looks like it's not showing up here, so we're going to have to make our own part. I'll search for it one more time. Maybe something was getting typed in wrong, but it looks like we're making our own thing. If I take this away, that doesn't give us anything. Oh, am I still searching in inductors? Let's try searching in all parts. Hold on. Ah, it does exist. That would have been so bad if I had just gone ahead and like made the part. So what's the difference between these two? The normal one and the G4. I don't know. Let's see. See if the datasheet has anything that says G4. Nothing immediately apparent. Oh, that's the wrong one. Hold on, which one am I looking at? WSNTR G4. Hold on. WSNTR G4. Okay, that wasn't helpful. Let me see if I can find a part number description. I'll show you what I'm looking at here. The, let's see, I'm looking for something different because there's the part and then the G4 version of the part, right? And if you look at all of these different things, they're all the same. So I don't actually know what's different. Oh, it's listed on their website as being same as that. They're the same thing. So, I wonder what the reason for that was then. Okay. Well then, let's just pick the one with the shorter part number. Place. And then we're going to need a little room here because this circuit looks really awesome, at least in the datasheet. And by awesome, I mean a lot of work. Should be fun though. I feel like we're going to have to learn a lot more. Okay, we need to find an example circuit and then start figuring out values. Low dropout single or two cell lithium ion lithium polymer charger. Yep, there it is. Okay. Well, they list all the parts off pretty exact. O257 WSNTR. All right. Oof, I'm tired. So capacitor, resistor. This status line, I don't think we're going to be doing the diode thing. I don't think we're going to pipe it directly into the micro. If I pull that up, let's see, TC pin out. Did I put... Charge status out. I don't remember what the story was behind that line. Oh yeah, there was a whole thing about this. All right, is there any other circuits? 0.5 amp charger using P-channel MOSFET. Once again, don't really care about that. About the status. I think this is a clever way to have two LEDs light up, depending on the situation, though. Using a PNP pass transistor. I tend to like MOSFETs better. Is the circuit actually more complicated, or does it just look more complicated? It is a little more complicated. All right, I think we use this one then. So, a couple capacitors, looks like 4 resistors, and then this transistor. So actually not that bad. And actually, I think we don't even need these. I think the temperature line... Oh, we might actually. Resistance input connecting the input to VCC divided by 2 disables this feature. So just do an even voltage divider here. Which is what we'll have to do. And 0.2 ohms to keep it short from happening. This resistor value, the RSNS, I wonder if we can change that. Because I'm a little worried by how fast this is going to charge. See, maybe we put a resistor in front of it, actually. That 2.2 ohm resistor is going to have a lot of, be able to dissipate a lot of power too. Applied through pin SNS maintains a voltage of V SNS across the current sense resistor. The following formula calculates the value of the sense resistor. Is the desired charging current, which we want to be 500 milliamps. So V equals IR, basically. And so at its worst case, we need to know what the worst case of the batteries is. To figure out this SNS value. Let's see. Don't need this one anymore. Okay, let me go. That's not it. Okay, this. Batteries, Adafruit 1781. What I need to know here is what the minimum charge is, like where the absolute bottom is when it's fully discharged. All right, here's our battery. Charger on a 1 amp. Spec sheet. All right. Discharge cutoff voltage is 3 volts. So that means the lowest it can get down to is 6, and the highest it can get up to is 4.2. So the beauty of lithium ions is they have such a small voltage change between full and empty. That's part of what makes it so hard to tell how much battery is left in them, though. Okay. So 3 volts is the bottom, so 6 volts is the minimum that it will be at. So you figure difference between 6 and 8.4 is 2.4 volts across this resistor, this RSNS. So now we just need to do our calculation. 2.4 divided by 0.5 is 4.8. So we need something with 4.8 ohms. All right, resistors. And then I'm going to go back up to this other circuit because this is the one I'm going to be creating. Oh, excuse me. All right, in stock, active. And we need milliohms, ohms. It's going to be semi-important that we get this kind of close. But we'll see what we can do. There may not be a lot of options depending on... .7 is a little small, but I think it could work just fine. What's the current if we use 4.7? V equals IR. So 2.4 divided by 4.7. 0.51. Okay, that's acceptable. Yeah, looks like we're using 4.7 ohms. Some of these I imagine are sizable because they are thinking that if you're using a thing this low, you need to dissipate a lot. What kind of power are we talking about there? Is that a... How do you know the max current of a resistor? I'm sure it has a max. A voltage limit or something. That's probably calculated based off of the power. I don't know, let's pick something at random and see. How complicated can the data sheet for a resistor be? Oh, a few pages at least. Tolerance, imperial size, rated dissipation, 2.25, 4.5. So what's our dissipation then? Because power is V times I, right? So we know that the max is 2.4 volts times 0.51, which is 1.2 watts. That's kind of a lot. I wonder if they even have something that is close to that. Basically, anything this or up is what we're going to have to use. Wow. These are expensive. I don't even know if they have footprints for them. That's cool. Well, it should be fairly easy to solder them, that's for sure. All right, let's see what we can find then. I mean, I like them all. Let's see if we can find a part. Nope. How about this one? Just keep picking random stuff until we get one. Nope. I'm trying to pick things that aren't horrendously expensive right now. Ooh, this one is, and it's cheap. The cheapest one here on DigiKey. So I think we're gonna use it. Is it the right value? 4.7 ohm. Yep, 5% 2 watt. Okay. Let's place this. Just over here somewhere. All right, so that's R3. So we need to go ahead and add this to the bomb. All right, this is 4.7 ohms. And a 2 watt resistor. Just to make sure. All right, excellent. I don't need that anymore. All right. So that's this resistor. So VCC and SNS need to connect between it. What's VCC in this? Can it do? Is this? I'm sure I've checked this already, but this better be a 3-volt part. Supply voltage. Oh, it could be anything up to 18 volts. Okay. Right. Output voltage is... Oh yeah, that's depending on the thing. Are we supplying 5 volts to this thing? Oh, I think we have to, because we can't supply... We can turn the 3.3 volt regulator off. So we basically have to supply 5 volts. Right, because it's coming in from the USB. Okay, so we're doing this off 5 volts. That's fine. All right, so anyways, between VCC and SNS. All right. What am I doing here? Between VCC and SNS. Boy, they're making this complicated, aren't they? All right. Properties. No. Properties. Please have a resistance. Yes. All right, turn that on, turn that off. Okay. All right, and then this comes over here. And then we need to drop a ground. Right here for VSS, I assume. Okay. I'm hanging in there. All right, so that's that first one worked out. We'll need a 1K resistor there. That should be a very low current. Just in standard 0805 part will work. And then should see if this part, what it looks like. Okay. Sizable diode. In stock, reasonably priced. If so, I'll use it. If it's available here in Circuit Maker. No, it's not. Okay. It can never be that easy. All right, we need to find a diode that closely matches, or not a diode, a transistor that closely matches this. BJT. Is this a BJT? I think so. Yep. All right, there's a lot of these in stock and active. All right, we're going to do a PNP. I'm just going to basically put in the same stuff that was in this other one and see what we get. Current max is 3 amps. So basically, let's just do 3 amps minimum. Okay. Wow, there's some pretty insane ones here. Bag, box, bulk. Let's not do bulk. Cut tape, tape and box, tray, tube. I want things that I can buy singles of. That's better. Also more expensive. Let's see if this one works maybe. I think most of these at this point would work. Okay. I think I just look through and try and find now. Let's see if any of these. Nope, that one's not available. All right, what about this next one? Three amps should be enough. Nope. Just going through all of the cheap options. This one does, okay. The picture that they're showing here does not match up with the picture that is shown here though, so. I really need to see what this layout looks like. Oh, excuse me. Nothing? All right. Oh, there it goes. Okay, the footprint looks correct to the part. This picture just looks weird. Maybe it's not though. Maybe they're drawing. Maybe the picture on the actual webs on DigiKey is weird. Not recommended for new designs when I pull up the data sheet. I thought I clicked active. We'll risk it. All right. This is going to be our transistor. We'll move this around. And then I think I have done a terrible job of continuing to keep... Oh, no, I have... Okay. I need to add this to the bill of materials. This is Q1. Value A. And then our description. Our part number. And our link. All right. So that's added. It comes in, goes out, connected directly to BAT, and then 1 kilo ohm resistor between that and CC. All right. This is complex enough. I'm going to pull this up. So here. All right, let's see where we can place this. Wow, this is kind of weird, actually. The way this is laid out, this symbol is laid out is weird. All right, I don't really think I need a part number on this one. So I'm going to turn that one off. Okay. All right, then this part is directly to BAT. Here, let's move this out a little bit. Okay. And then this one goes to the sense. All right. Here we go. Should be connected. All right. And then we need a 1K resistor. Just some standard 0805 part will be fine. And 1K is a really common value, so I don't imagine this will be a hard one to find. Okay. Wow. Did I click on a weird version of this or something? Some of these are really expensive. Like really expensive. I just want something that comes in cut tape. Here we go. Panasonic electronic components. I don't mind their stuff at all. Hey, and there's a symbol. We'll take it. All right, let's place that. Drop that right there. Whoops. Pretties. Resistance, turn that on. Turn off part number. Okay. And we'll put that right there. And then the wire needs to run between that and CC. No, no, no. Ah. What is this? Okay. So that's that part worked out. So now this will charge the battery just fine. Now we need to solve our temperature sensor. I wish I could just use the same part, but I really want to use 10Ks for that. Kind of minimize the power loss. So basically we have to put an even voltage divider here so that this sits at 2.5 volts. And that will make sure that it's disabled. Let's see. What was I going to say after that? Then make sure that's disabled. Oh, we need to check the input impedance. See if that's a thing. Basically, input pins like this have an impedance associated with them, how much resistance they have. Our voltage divider circuit's going to work, but if we don't take that into account, it can sometimes affect what the measurement will be if it's really low. They may not even have it listed because it'll be so high that it won't matter. But it's always good to look just to be safe. Temperature. Yeah, it doesn't have it listed. That's okay. That means we should just be fine. As long as we use a reasonable resistance, so 10Ks. I think we'll be okay. All right, so go back here, change the resistance. To a 10K part. 10K is also very common, so. And there's a fair few. Let's just stick within the same company, Panasonic. All right. Hey, there is a model. Cool. All right, we're gonna need 2 of these. All right. I don't think I've been updating the bomb. I always remember. Yep, I haven't been. Crap. Hold on. Honestly, this circuit's turning out to be a little easier. It's kind of weird. All right, what is this part? Okay, and then I'm gonna put everything in here. All right, and then this one we know is a 1K. This is a 10K ohm. And if we ever have to use 1Ks or 10Ks for the rest of the project, we can just add more into this thing here. All right, so our 1K description. Let's see. Description for this. Part number. You may be able to tell kind of how their part number works when you see this, because they're very similar, except for the 102 and 103. So 2 stands for 2 zeros. So 1 0 and then 2 more zeros, 0 0. So 1,000 or 1K. 1 0, 3 zeros, so 10,000. A lot of manufacturers do resistor part numbers like that. Okay. So got those in. Wow, really? No properties? All right, so we'll add 10K to both of these. Show that. Hide that. Okay. Show that. Hide that. Okay. There we go. And then there's got to be a faster thing for rotating this. Rotation is 90. Properties, rotation is 90. Okay. This wire is really annoying, so I'm just gonna delete it and just label it, because having it work its way around is really hard, is getting really annoying to see and work with. Okay. That can go there. That can go there. And then we'll label this side too. Label. Oh, come on. We're going to name this, oh shoot, no, we need to name this, hold on. I think there's something up here that will tell us. Yeah, this right here. USB 5V, that's what we need to name it, definitely. Yep, okay. Because that's power coming in from the USB. All right, and ground. That can go there. Oops. Oh. Here and here. Here to here. And then this one up here will have to be also... And this is USB 5E as well. Okay. Wow, we might actually finish this one today, too. It took us so long to do that last time, and this just, I thought this was going to be the hard circuit. And we are moving through this. We got the 4 resistors. We'll need the capacitors still. Alright, let me pull it back up here. Yep. Okay. So we're missing capacitors. We need another capacitor. We need a capacitor on VCC. And then comp needs to be connected to VCC. Have we done that already? No, we've not. Okay. So let's slide this out. Hold on. Oops. No, don't do that. Alright, before we do anything, let's save, because it's been a while. Save all. Okay, just in case we lose it. It's there now. This needs to go to that USB 5E. I guess I could just draw it across. It won't be that confusing. I don't like having wires crossing in schematics, but it's not always avoidable. What is C comp? Charge rate compensation input. It says the charge rate compensation level. The voltage regulation output may be programmed to vary as a function of the charge current delivered to the battery. So I guess in this version of the schematic, we just tie it high and call it good. Oh yeah, it's used in the MOSFET version. Oh, okay, so you can control the rate at which it charges. Interesting. We're just going full. Man, if I had these circuits, if I had this chip, it would be a lot of fun to play around with and figure out how exactly this thing works and what the kind of different stuff you can do with it. But I just don't have the stuff with me or the time to do that. Alright, so that's good. Then the last thing is the capacitor on VCC. We need 0.1 microfarad. Do we have any of those already? Are we using any 0.1 microfarads? No, 10 microfarad, 1 microfarad. We need to go down another order of magnitude. Bigger would probably not hurt here. But where are those capacitors to? Are they already on the USB? Yeah, 1 microfarad. Okay, so yeah, it's already going to be helping it a little bit, but let's just go ahead and find one. C3. Alright, ceramic capacitors. Does anyone remember when a few years ago there was a capacitor shortage? That was really annoying. I had to deal with so much ridiculousness at work because of that. Just couldn't find parts to build anything. Alright, 0.1 microfarad, 0805. And they just pick something that's cheap and they have a lot in stock. Oh, let's get a cut tape. Here's a nice little 10-cent part. Let's see if we just gotta find one with a footprint. Hey, it does. We're using it. Drop it right there. Alright, let me add it to our bill of materials. If we're lucky, I'll be able to find all the parts on one website. And that will save me a huge amount of headache. All right. Okay. Properties. 90 degrees. Show the capacitance. Hide the part number. Is that upside down? It doesn't matter, but... Okay. All right, so that's that capacitor done. And then, okay, so this last one, I don't think we're going to do here. So basically, we have all these parts here, except status. I need to label that one. Note this capacitor right here. How it's next to the battery. That proximity, I believe to be important. I don't think there's anything in here that tells you like how to pick it or something. Huh, interesting. But basically, these are basically what are known as debounce caps. They kind of smooth out the voltage near components. The reason there's one next to the chip is so that you don't have a shaky power line going into the chip. It helps to smooth out that line so you have a good supply for the chip to run its logic on. Because this one's over here next to the battery, rather than put it on the schematic next to the chip, like, see the battery line's out right here. Rather than put it there, I'm going to put it near the actual batteries themselves. So we say 8.4 AV4 there. Where's our 4.7 ohm resistor? Am I missing something? Here it is. SNS. We may have to change the name of this. This is not SNS. This is 8.4. So that they're connected. Yep, AV4. I just realized that would have been horrible if we didn't connect those up. Circuit just didn't work. Okay. And then this line, we'll name this something. I hate the way it does that. Battery AV4. Okay, and so now we have to put down batteries. I really hope that that connector they use is already in here. If it is, that would be great. So, voltage boost, recharge, this thing, the connectors. This is an interesting part number. It's on DigiKey, just not in this country. Let me see if I can find it on DigiKey. 0 in stock. Typical. Arrow. Mouser? Non-stocked, call for quote. Okay, that's aggravating. Well, I don't really have a choice with them using those connectors on the battery. Does Arrow sell stuff like a few at a time, or is it all in reels? Not buying it there. All right, well, let's see if it exists here. We'll put it down for now. We can change it later, but we need to get the basic part down. Nope. Nothing present. All right, looks like we're going to be making something. That's exciting. All right, I want to work. I don't want to start this right now. I'll probably work on this next time. Yeah, I think this is going to be a good place to stop. Let's see what else we got to do. Oh, you know what? How about that USB connector? The USB-C connector. Let's see if that exists. A in stock somewhere and B in Circuit Maker. Yep, it is in stock in DigiKey, so that's cool. Because I can at least drop that down. Nope, they don't have a thing made for that either. Alright, so that'll be next time. And making parts is actually quite involved, so probably won't get that whole thing done. There's a regulator. What did I label this circuit, this schematic? Power supply, okay. So I'm trying to fit everything on that fits under all the way up to here. Yeah, all right. Sorry, I'm just spacing out there, but I think all of that works. So there we go. Let's see. Anything else I need to do before I sign off? I think I'm good. All right, well, if you have any ideas or anything, tweet them at me or let me know. There's a lot that needs to be done here, so. But we're making progress. This looks good. This part right here, at least. Even though it's not much, it took a lot just to get this much done. Let's see, I'll move this whole thing over. Actually, move this down. Slide this down. Put the USB-C port here, and then all the connectors over here, and the voltage regulator here. Should be pretty straightforward. All right. Well, thank you all for joining me. And I will see you next time on Tuesday. See ya.